Did you know that every time you call a friend, you're actually having a conversation through light? And that light is guided through fiber optic strands, thinner than a human hair. This material, fragile as it may seem, is in fact stronger than steel when it comes to carrying data. Yet, the journey of creating a single fiber, starting from pure quartz sand and ending as massive cable coils laid deep on the ocean floor, is one of the most intricate industrial processes in the world. In this video, the Factor-In takes you inside state-of-the-art production lines to uncover how millions of optical fibers are made and why they've become the backbone of the connected age. History of fiber optics. The United States was the first country that brought fiber optic cables across the ocean. In 1988, the TAT-8 line went into service, which connected America with the UK and France. And that moment marked the beginning of a new era of global connectivity. From that milestone, the US became the heart of the world's internet infrastructure. What made this huge leap possible were American tech giants such as Google, Meta, and Microsoft, who do not only use the internet, but also invest in it, and even co-own some of the most important cables on the planet. So what do you think? If fiber optics did not exist, how would our lives look today? Raw material extraction. To create fiber optics, the process begins with high-purity quartz sand. Only carefully selected deposits of white sand are suitable, since they contain the level of silica required for optical glass. At the mining site, tracked excavators work continuously, scraping away thick layers of sand and loading them onto heavy trucks. Each load can carry dozens of tons, transporting the raw material straight to a nearby processing facility. There, the sand is poured onto conveyor belts and passed through vibrating screens that separate out larger stones and organic debris. It is then moved into industrial washing tanks. These tanks use powerful streams of water combined with mechanical agitators to wash away clay, fine dust, and bits of vegetation. The washing cycle is repeated several times until the entire batch reaches the desired level of cleanliness. Wastewater from the tanks is fed into a recycling system, which recovers fine silica particles carried off by the flow and minimizes material loss. Once the sand meets the requirements, it is dried in industrial furnaces to remove all remaining moisture. Finally, it is packed into sealed containers, ready for the chemical stage, where the silica will be transformed into gaseous or liquid compounds before being formed into the optical fiber that becomes the fiber. Fiber optic manufacturing. From sealed containers of pure silica, the material is moved to the chemical processing area. Here, technicians convert silica into gaseous compounds under high temperatures. These compounds react and condense into layers of ultra-pure glass. Instead of melting sand into a solid block, this technology builds the glass layer by layer, gradually removing nearly all impurities. The process takes place inside a hollow glass tube that rotates slowly while being heated by a moving torch. As the gas mixture passes through and meets the high heat, it transforms into microscopic silica particles that settle onto the tube wall and form the desired structure. By adjusting the gas composition, engineers can determine which section will become the core, where light will travel, and which section will form the surrounding cladding. Each layer is tightly controlled for thickness and purity, since even the slightest deviation can affect how well the fiber transmits light. Because of these strict requirements, preform fabrication is also the most expensive stage in the entire fiber optic production line. The raw materials must reach near perfect purity, and the deposition process can take dozens of hours for a single preform, making it far more costly than other steps. After many hours of continuous buildup, the glass tube gradually solidifies into a dense solid rod known as the preform. A typical preform is about 3 to 6 feet in length and a few inches in diameter, and inside it already contains the complete core and cladding structure of the fiber, only on a much larger scale. When the glass preform is ready, it is moved into the fiber drawing tower, a steel structure that rises more than 60 feet tall. At the top of the tower, the preform is held in place and fed into a special furnace. The temperature inside can reach nearly 3,600 degrees Fahrenheit, hot enough to soften the bottom of the preform. As the glass begins to flow downward, a small drop is pulled into a thin strand, marking the start of continuous fiber production. From that point, the entire system operates under tight control. The strand is drawn straight down, with a diameter of only about 0.005 inches, thinner than a human hair. The key is to keep the fiber uniform from start to finish. If it becomes thicker or thinner by even 1/1000th of an inch, its ability to transmit light can be compromised. To maintain precision, multiple laser sensors along the tower scan the fiber continuously, measuring the diameter of each section with high accuracy. During this stage, operators often use pliers or small blades to touch or cut the fiber directly. This step is necessary to remove the unstable portion at the beginning or to cut a sample for quick inspection under a microscope. Sometimes they also cut the fiber at the end of a run to separate the product from the machine. These actions ensure that only fibers meeting the standard move forward to the next stage. The drawing process can continue for hours on a single preform. From a rod just a few feet long, the factory can produce optical fiber stretching for dozens of miles with consistent quality and purity, ready for the following steps of the production line. After being drawn into a continuous strand, the glass is still extremely fragile. To ensure it can move on to the next stage, the factory immediately applies a protective coating. The fiber passes through a small chamber filled with liquid polymer. This polymer is specially formulated to create multiple layers. The inner layer is elastic to reduce cracking when the fiber bends, while the outer layer is harder to resist impact and abrasion. Next, the fiber runs through an ultraviolet curing system. The UV light hardens the polymer, instantly turning the liquid into a transparent protective layer. This step is fully synchronized with the drawing speed, ensuring the coating has a uniform thickness and a firm bond. With this protective layer, the optical fiber can withstand handling, transport, and testing without the risk of damage. After the protective coating has been applied and cured, the fiber is guided through several automated inspection stations. Laser sensors monitor its diameter and uniformity, while optical devices measure signal transmission. This takes place continuously along the line to ensure the fiber is stable before moving on to the winding stage. At the winding area, the fiber is fed onto massive reels located at the base of the tower. Each reel can hold dozens of miles of fiber, wound at high speed while maintaining steady tension. If the fiber is pulled too tightly or overlaps unevenly, it can crack or deform, so the entire winding system is precisely programmed and carefully monitored. A mechanical arm guides the strand back and forth, laying each loop neatly side by side in uniform layers, much like winding thread, but on industrial scale. Operators closely watch the display screens for tension and speed, ready to intervene if anything goes wrong. When one reel is full, the system automatically splices the fiber onto the next reel, so production continues without interruption. In this way, a single preform can produce continuous reels of fiber that are later packed into protective containers for safe transport, from the spools of fiber that have already been coated and tested.
The factory begins the cabling process to form the finished product. First, multiple reels of fiber are arranged in parallel and fed into a massive cabling machine. Here, the fibers are gathered into bundles, usually ranging from a few dozen to several hundred strands, depending on the transmission capacity required. Between these bundles, manufacturers add reinforcing elements made of steel or Kevlar to increase mechanical strength. Kevlar is particularly valuable because it is lightweight yet many times stronger than steel in tension. Next, the entire bundle is wrapped in additional protective layers. An outer plastic sheath helps block moisture and provide insulation. Some cables also have a water-blocking gel pumped inside to prevent leakage and signal loss. For undersea cables, the construction is even more complex, with multiple layers of steel wires wound tightly around the bundle to withstand deep-sea pressure
and resist damage from ship anchors or seismic activity on the ocean floor. The cabling machine operates in a precise rhythm, twisting the components evenly around the fiber core to maintain uniformity along miles of cable. Operators carefully monitor the tension and winding angle on display screens, since misalignment or excessive compression could cause the cable to fail when bent. Quality testing. After the cabling process is complete, the product must undergo a series of tests to ensure it can operate reliably for decades. First come the basic mechanical and environmental tests. The cable is stretched, bent, and twisted to check its strength, then placed in thermal chambers that cycle from deep cold to extreme heat, or submerged in high-pressure tanks to simulate deep-sea conditions. Next are optical tests, where a laser beam is sent through the core to measure signal loss. These steps quickly reveal any production flaws or substandard materials. However, to prove that the cable can truly function in real-world conditions, the factory carries out full-length testing. Engineers connect both ends of the cable to optical transmitters and receivers, sending data continuously for hours. It is not just light pulses. The system transmits video, voice, and network traffic to mimic actual operation. If the signal passes through the entire length without packet loss, distortion, or abnormal attenuation, the cable is considered ready. In addition, the cable is run under continuous load for extended periods to test long-term stability. Some samples are even installed in real field conditions, such as being buried underground or strung on utility poles, and their performance is measured after days of operation. This step is crucial because only through real-world trials can the manufacturer be certain that the cable will withstand 24/7 use for many years. Once the cable has passed all rigorous testing, the spool is officially considered a finished product. But before it reaches the installation crews, it must go through packaging and transportation, an equally critical stage. At the factory, the cables are removed from the testing machines and placed on large rotating shafts. From there, they are rewound into neat coils on massive drums made of steel or reinforced wood. Each drum can measure several feet in diameter and hold hundreds of miles of continuous cable. The winding must be performed carefully to avoid excessive tension or sharp bends, since even a minor kink could degrade signal performance. After winding, the cable ends are sealed with protective caps to keep out dust and moisture. Every drum is labeled with its batch number, cable length, structural type, and inspection results. Engineers then carry out a final check to ensure the spools remain intact during movement in the warehouse. For transport, the drums are loaded onto heavy-duty trucks or specialized shipping containers. When shipped by sea, they are placed aboard cable-laying vessels, specialized telecom ships equipped with multi-deck storage for dozens of giant drums. Steel securing systems lock the drums in place, preventing any shift during voyages that may stretch for thousands of miles. This process of packaging and transportation ensures that every spool of fiber optic cable leaves the factory in perfect condition, ready to be deployed in infrastructure projects, whether across bustling cities or laid deep along the ocean floor. Undersea installation. Once the fiber optic cable has been delivered to port, the task shifts to specialized vessels known as cable-laying ships. On deck, massive drums are mounted into a feeding system that carefully releases the cable into the sea. The strand is guided through tension control devices to ensure it descends safely to the ocean floor without bending or breaking. The operation is deliberately slow, often just a few miles per hour, as the ship must follow a pre-surveyed route in deep waters. In deep waters, the cable is simply laid on the seabed, but near shorelines or in areas at risk of anchor damage, plowing machines carve trenches into the seabed so the cable can be buried several inches below. Engineers aboard the ship continuously monitor the process using sensors and underwater cameras, ensuring the cable is laid in the correct orientation and without twists. Once complete, the line rests securely on the ocean floor, linking continents at the speed of light, informing the backbone of the global internet. Conclusion. From pure white sand to cables lying deep beneath the ocean floor, the journey of making fiber optics is proof of how far human ingenuity has gone to connect the world. Every single meter of cable passes through dozens of demanding steps: purification, fiber drawing, coating, cabling, testing, and finally being shipped and laid by specialized vessels. The result is a vast highway of light that allows billions of people to communicate, learn, work, and enjoy entertainment with just a simple click. Today, thanks to fiber optics, a call across continents travels in less than a second, and the movies you stream arrive almost instantly. What feels ordinary in our daily lives is actually powered by one of the most complex industrial processes on Earth, one that most people never get to see with their own eyes. If you found this journey fascinating, drop a comment below and share your thoughts. Don't forget to hit the like button to support our team and subscribe to the channel so you won't miss the next deep dive into the world of modern technology. Every click you make is the motivation that drives us to keep uncovering the hidden stories behind massive industries.